Hello, everybody. My name is Aniat, and today I'll be covering the problem number 1, Asymptotics Potpourri. In this problem, we need to give a tight runtime bound for mystery as a function of n, where n is the length of the input array. Let's look at the definition of the function mystery. So its signature is pretty simple. It accepts an integer array, and after we create a boolean done, which is going to be equal to false at the start. Our while loop is going to have this condition, and it's going to terminate if our done is equal to true. After that, we are going to change the value of done to true and iterate through every value in our array using a for loop. And here, we're going to perform a simple swap. After that, we're going to return our array after we finish sorting. Let's look at the example that I drew on the right side of the screen to better understand the behavior of our function. If we fed in an array consisting of these values, which I picked on random, on the first iteration, we will do this comparison, which is, of course, this if check. So if array 0 is larger than array 1, which would happen if our I is equal to 1, we know that this is false because 3 is not larger than 4. Then our I gets incremented by 1, and if our I is equal to 2, we're going to perform this if check, which is, of course, when we're going to compare the values of 4 and 1. So we know that 4 is larger than 1. Therefore, we're going to get inside of this if function. And here we are to make following changes. So we are going to change done to false from true. And after that, we create integer temporary, which is going to be equal to array 1, which is equal to 4. And after that, we change array 1 to 1 and array 2 to 4. Therefore, our initial array is drawn here, and it's going to be something like this after our first swap. Now we're done with everything in the if condition, and our I again gets incremented by 1. So and when our I is equal to 3, we're going to perform the same operation of swapping. So this time we're going to be working with those two values of 4 and 2. And of course, since 4 is larger than 2, we're going to swap them. And our array is going to be 3, 1, 2, 4. But as you may have noticed, this is not sorted. Therefore, we're going to go through another iteration of while loop, and therefore perform all of the operations that we did before, starting from I equal to 1. Therefore, our array is going to look something like this after the first if check, and it's going to be completely sorted after the second iteration of while loop. Let's look at the second example. So what would happen if I fed in an sorted array, which has the values 1, 2, 3, 4? So we will create a boolean done, which would be equal to true inside our while loop. And after that, we must notice that in the for loop, if condition would never be equal to true. It would never be equal to true because every value that we have is smaller than the one next to it, or the one that is on the right side of it. Therefore, if we consider it like more general case, it would look something like this. So our integer is equal to a1, a2, a3, an, where a1 is smaller than a2, which is smaller than a3, which is smaller than an. We know that array I minus 1 would always be smaller than array I. because A1 is smaller than A2, which is smaller than A3, which is smaller than any value on the right side of it. Therefore, we will perform only one for loop, which will take an amount of time. Why n? Because we change our I from 1 to array.length. Therefore, we will do n iterations in total. So the intuition here is that if our array is essentially sorted, we will perform only this for loop without doing any if checks. No, I meant anything that we have in the body of the if, which would of course take n units of time. And so we can say that in the best case, we're going to perform no, actually, let me rephrase myself. We can definitely say that big omega, or the best case runtime, is equal to n. Now, let's look at the opposite condition. So what will happen if our integer array has the values A1, A2, A3 until AN, where instead of following this rule, we will follow this rule, which of course means that A1 is larger than A2, which is larger than A3, and etc., until we reach the end. So let's look at what will happen after our first for loop. So after our first for loop, A1 will get swapped with A2, and after that, A1 will get swapped with A3, and A1 will get swapped with A4 until our A1 will get transferred from the zeros index to n-1 index. And after our second for loop, we will do essentially the same thing, and A2 will be in this spot. And after that, A3 will be on the like second to last spot, and etc., until our array will be sorted. Therefore, we must look at what amount of work we do and in each of these for loops. So we know that this for loop as a whole takes n unit of time. Therefore, since we executed it here, we were going to take like n units of time in total. So let me write it down. And after the second for loop, we also do an amount of time because we kind of screen through every value here using the for loop. And the third iteration of for loop also takes n units of time. So the question is, how many times do we need to run the for loop? The answer is n times, because we are essentially looking for an array that would look like this. And of course, it requires our for loop to be run n times. So the answer is n multiplied by n squared. Our big omega runtime is equal to n squared. Let's go back to the previous page. So here we said that the best case is big omega of n, and the worst case is big omega of n squared. And therefore, we're not going to have a theta bound because big omega and big O, I meant, and big omega are not equal. This is all for problem number 1.1.